Guys, tonight, page 569, number 4, 5, 6, 7, 9, and 10a. We're going to look at a few of those questions today, starting with question number 4. There's a point in the Earth's atmosphere, the electric field is 150 newtons per coulomb downward, and the gravitational field is 9.80 newtons per kilogram, or could be meters per second squared, right, for gravitational field, also downward. What's the electric force on a proton placed at this point? Well, the electric force would be equal to Q times the electric field. Okay, this proton is experiencing the electric field. Let's use the experiencer equation. Q times E, we're going to say 1.60 times 10 to the minus 19 times the electric field strength of 150. That should give us, what, 2.40 times 10 to the negative 17 newtons. 2.40 times 10 to the negative 17 newtons. So talking about a pretty small force there, right? What about the gravitational force on a proton at this point? The gravitational force is going to be found by my force of gravity equation. F is equal to m times g. My mass is 1.67 times 10 to the minus 27 kilograms times my gravitational field. Be careful about this because we're used to using 9.81. We're saying in this case, the gravitational field is 9.80 because we're a little bit higher up in the atmosphere. Do the math there. I'm not sure what exactly that works out to be, but somewhere around 1.6 times 10 to the minus 26 newtons. Which force is bigger? The electric force. We usually expect the electric force to be bigger than the gravitational force, right? All right, next question, number 5. Says a metal box is charged by touching it with a negatively charged object. Compare the distribution of charge at the corners of the box with the faces of the box. This is the metal box. The corners of the box will have a charge distribution that is different than the faces. How so? Yep.
The corners have a greater charge compared to the face.
Yeah, the corners have a greater concentration of charge. It's not that the faces don't have charge, but it's going to be more concentrated at the corners because they're pointy, right? The face is uniform, so we get this nice uniform distribution along the faces, but pointier at the corners, so therefore a higher concentration of charge. Yep.
I'm just curious, but can you actually observe fields, or do we just
Yeah, no, that's a good question. Can you actually observe fields? Well, fields are actually like a human construct. Okay, we invent the concept of fields to describe electricity. So no, you can't directly observe fields. Now, if you put something, little charges that you could see in that field, you would observe the direction those charges went. Positives would go with the field, negatives would go against the field, either with me or you're against me. But you wouldn't observe the field itself because that's a human construct, okay, that just describes that allows us to visualize what's happening there. All right, draw the electric field lines inside and surrounding the box. Well, the field lines surrounding the box, you're going to notice at the corners are closer together because the charges are closer together. And with charges closer together, you get a stronger electric field. Along the face of the box, you're going to get the field lines a little bit further away from each other because it's a weaker field. Weaker field because we got more spreading out. Now, inside the box, we would have field lines going. Now, everywhere you have a field line outside the box pointing inwards, you'd have an electric field pointing like this, countering it. Now, the difference is inside the box, these field lines all end up canceling out. Outside the box, these field lines don't cancel out because they're in different locations. Okay? That leaves us with a net electric field of what inside the box? 0, right? We know that the charge distribution in or on conductors, well, it's always on conductors because you got a conductor with extra charge. It always goes to the outer surface, always goes to the outer surface. If it's uniform surface, it's evenly distributed. If it's a pointy surface, then we have a higher concentration. And of course, we know that the field inside the conductor is always going to be 0. All right, next question, number 9. Number 9 says determine the magnitude and direction of the net electric field at a point P shown on the diagram below. Well, let's look at the field caused by the positive. Which way is it going to point? To the right or to the left? Away from the positive or toward the positive? It's going to point away, so it's going to point to the right. Good. Now, the electric field caused by the negative charge is going to point which way? The blue one, left or right? It's going to point to the left because it's going to point toward the negative. So we've got to find out what both of those fields are. E is equal to KQ over R squared for the red one. 8.99 times 10 to the 9 times 50 microcoulombs. I would not suggest just moving the decimal place over for this. Okay, if you're like me, you're going to probably mess up on that. I'm just going to say 50 times 10 to the minus 6 coulombs and divide that by the distance of 0.45 squared, right? 0.45 because we want the total distance between point 1 and point P. Do the math, we get 6.2361 times 10 to the 12, and we could say newtons per coulomb, or we could say volts per meter. Either one of those would work. Now for the blue one, the negative charge, we're going to also say E is equal to KQ over R squared, 8.99 times 10 to the 9 times Q, which is 10 microcoulombs, 10 times 10 to the minus 6. It's a negative charge, but we're dropping the sign of the charge. The only reason we needed to know that it was negative was to determine the direction of the field there, and that was toward the negative there. Logan? Why did I put a what? Oh, that should have been positive 9, yeah. In my calculator, I put a positive 9. So that is the answer, I think. Yep. I said 8.99 times 10 to the 9 times 50 times 10 to the minus 6 divided by 0.45 squared. So that's correct. I just put a negative 9 there for whatever reason. We're going to divide that by 0.15 squared. And that's going to give us, yeah, this one should be 3.9956 times 10 to the 6 newtons per coulomb. And this one is incorrect. This one should be 2.2198 times 10 to the 6 newtons per coulomb. Now we're going to add these together. Making sure the red one is positive, 2.2198 times 10 to the 6. And making sure the blue one is negative, negative 3.9956 times 10 to the 6. We do the math there and we end up getting, when we do that, negative 1.78 times 10 to the 6. We say newtons per coulomb, or once again, we could say volts per meter. And finally, number 10 says a uniform electric field exists between two charged plates. We want to find the electric field between the plates. All we're going to do for this one is say E is equal to delta V over delta D. We have our experience or equation that we're allowed to use. E is equal to F over Q. And we also have our producer equation, the producer equation for uniform fields. This one. This is the one we're going to use. 12 volts divided by 6 times 10 to the minus 4 meters gives me 2.0. 12 divided by 6 is 2 times 10 to the 4. And the units would be volts per meter, or you could have said newtons per coulomb. That would have been fine as well.